variables that we actually wish to investigate. Okay. So a bit of revisit. If you still recall, we actually have a lecture 1 on the basic probability notations and also counting, including the permutations and combinations. And then we also talk about conditional probabilities, marginal probabilities, and in the other day, Bayes theorem. Okay? And this Wednesday, we're going to discuss about the tutorial on Bayes theorem. So please make sure you have tried it before we start to discuss the answer, right? Because if you don't try it, I mean, you don't really hands-on, it's actually very difficult for you to catch the meaning of the concept. So we start with discrete random variable. Discrete random variable takes on integer values, usually the result of counting. Of course, taking integer value is actually not a must, but most of the time, the example that we are actually looking on is actually integer values, right? For example, over here, we flip a coin and count the number of hits. The number of hits result from a random process basically is flipping a coin over here. And what is your outcome? It's actually head or tail, right? Because over here is either, and then you can actually represent it as 1 and 2 or 0 or 1, okay? In terms of your representation if you want to. But there's also one thing which is called number of hits, okay? Number of hits over here is based on your outcome that you actually get after you flip a number of times of your coin, not just one time. You perform a calculation over here, and this is also can be considered as a random variable, and it's actually discrete random variable because every time your number of hits is actually represented by an integer value, and whenever the hit occurs, it basically executes +1, right? So in that case, the potential outcome is actually between 0 and +infinity. But this +infinity is actually dependent on the number of flipping that you have, right? It's actually bounded. So in that cases, every time when you flip a coin, minimum chances for you to get a head is actually the number of heads that you actually get is actually 0. But if you are actually flipping 10 times, for example, maximum times you can get a number of hits is actually 10, from 0 to 10. So basically, if you want to formulate it in a way, it basically equals to 0 to n, and n equals to the number of times you actually flipping a coin. Okay. And why I'm saying that it can be not integer values, because if you are actually measuring in terms of time, but you actually use some timestamp, for example, you try to measure the probability of something happening, but you are actually having a fixed outcome. It can be like half a minute, 1 minute, 1.5 minutes, and so on. So you notice that there's actually 0.5, 1, or 1.5, but you have a clear step. Then it's also acceptable to be a discrete random variable at one point. Okay, because you have a clear cut or clear numbers of outcome that is actually possible for that particular random variables. Unlike continuous random variable, you have unlimited potential outcome given a range. Okay, so that's why a probability distribution is actually represented in the 2 different ways. For probability distributions for discrete, this looks like this. This looks like a histogram. And sometimes you also see something like this. Okay, if it's 1, 2, 3, 4, right? Maybe you will see something like this. It's possible as well. Okay, different paper might draw in a different way. Okay, different paper or different reference book. Okay, but it's actually these 2 are referring to the same thing. Okay, and continuous probability distribution will be represented by a curve, and this curve, for you to calculate the actual probability, you need to calculate the area under the curve. And that's why your integration comes in, if you still recall your integration in your maths class. So the probability distribution of a discrete random variable can always be represented by a table. So if the table, like the truth table, okay, if you still recall, I have drawn it like, I can't recall, it's a week 1 lecture or tutorial, okay? When I'm drawing a truth table for a head and tail for tossing a coin for 3 times, okay? And then there's actually 8 possible outcomes. That's the reason why a discrete random variable can be always represented by a table, okay? A simple exercise can have the 4 possible outcomes, which is over here, this example is flipping 2 times. What does it mean? It's actually trying to tell you that, you can actually have T, H, T, H, T, H. So this is your potential outcome. This is how you draw your table. It's similar to your truth table last time when you are studying in your I think it's the first year class, I can't recall. CSO, I think it's CSO. Now let's the variable x represent a number of heads that results on the coin flips. So the variable x can take the value 0 to 2. Because why? Number of heads, okay? Right now again, you're calculating number of heads. So this one is actually 0, this one is actually 1, this one is actually 1, this one is actually 2. When you take this all together into account, so all the potential outcome is actually 0, 1, 2. Okay. So, and then we move on. The table, it can look like this. The table below shows the, somebody can maybe mute your microphone. Anyone didn't mute? I'll need to go and mute all first. Okay. Anyone didn't mute? Okay. Sorry, I'll need to mute you all first, yeah? Okay, we continue. The table below shows the probabilities associated with each possible value of the x. The probability getting 0 heads is 0.25, 1 head is 0.50, and 2 heads is 0.25. Why is it so? Because when you are actually calculating all the specific, okay, so use the word specific easier, potential outcome over here, every one of it is 0.25, 0.25, 0.25, because everyone is having a fair probability. It's a fair coin, right? So 1/2 times 1/2, so you get 1/4, which is 0.25. Same goes to the others. So in that case, remember right now the probability that you want to measure is number of heads. So in that case, this is 1. Sorry, this is 0. This one is 1, and this one is actually 2. So in that case, that's the reason why you will get 0.25 for 0 heads, 0.50 for 1 head, and 0.25, 2 heads. You need to sum up the possibility over here. Okay? And given a probability distribution, you can find cumulative probabilities. So over here, it's actually probability 1 by 1, right? But when you're actually calculating in terms of number of heads, you can actually calculate a set of probabilities one shot. For example, over here, you're no longer, for example, calculating x equals to 2, for example. Oh, the example here is 1. Sorry, yeah. The example is over here. You can actually calculate x equals to 1, but over here you can actually calculate x smaller or equals to 1. Which this x smaller equals to 1 will be resembling, maybe this one. Okay, probably x equals to 0 plus probably x equals to 1. And eventually, you sum up these two together, you get 0.75, which means that probability of x small equals to 1 equals to 0.75. Cumulative probability distribution. So previously is a probability distributions, right? In discrete, we are calling it PMF, probability mass function. If in continuous, we will call PDF, not portable document format, probability density function. Okay, and for this one is again it's a similar cumulative mass function, and then another one will be cumulative distribution function. So random variable attribute, you always have some measurement for it to represent the curve or the shape of your distributions. And for you to represent it, usually you are using a central tendency and also variability. And central tendency is not is actually quite familiar to you. Basically, it's mean, mode, and median. How about variability? Standard deviation and variance basically is try to tell you that how far away your data actually can be scattered. For example, central tendency. Okay. Central tendency basically tells you that, like for example, if your curve is like this, or it's like this, or it's like this, because it tells you where your mean is. So this part will be basically your central tendency. But your variability basically will tell us how steep your curve is. Okay. Of course, my drawing is bad, but you can roughly know that there are different levels of variability over here. Okay, from a very small one into a medium one into a very large one, depending on the curve that you actually looks like. Okay. And the mean of the discrete random variable x is also called the expected value. There's actually another name for this one, which is expected value, but it's actually giving you the similar meaning of a mean itself. Okay, mean, expected value, giving you the same meaning. Okay, so in the class we will basically use these two terminology interchangeably, but it's actually the same. And the expected value of x is denoted by ex, which is over here you have ex equals to mu x. It's actually the same because the summation of x1 times probability of x1. So you notice that, oh, this is actually a probability over here. But actually, the idea is actually same for you to calculate the way that you calculate your ordinary mean. Okay. For example, you are actually if you have a number of data, you have where is it? You have 4, 4, 5, 6, 6, 6, for example. And then if you have 1, 2, 3, 4, 5, 6, then you basically divide by 6 and then you get your answer, right? And then you get your answer. But how about this one? It's basically 1, 2, 3, 4, 5, 6. You have 6 data, right? Over here. So for you to get 4, it's actually 2 over 6, right? Plus 5 times 1 over 6, plus 6 times 3 over 6. You see the difference over here? This one is your ordinary way to calculate your mean. This one, how am I getting all these 2 over 6, 1 over 6, and 3 over 6? Because 4 happened 2 times, 5 happened 1 time, and 6 happened 3 times. And it's actually having 6 times. So I just put it down, and put it down. It's actually resemble the same outcome. You can try yourself, and then you actually get the same answer. All right. So this is how this formula comes in. Because there is a possibility that you don't really have this kind of data given to you, but you still need to calculate your mean or expected value. And this probability actually tells you that how probable this set of this data is actually happening. And if you try to convert this 1, 2, 3, 4, 5, 6 here, these 3 probabilities, when you try to convert it to the actual data, it's supposed to resemble like this. Or if you have 12 sets of data, then it's supposed to be like, oh, you have 4, 2, 4, 4, and then 5 will happen 2 times, 6 will happen 6 times. It's supposed to do it this way, okay? So this probability will basically tries to simplify or summarize what is your data behavior is. That's the reason why you actually have this kind of equation. But it's actually identical to the way that you're calculating means previously, just another formula, but it's using probability. The median of the discrete random variable is the middle value, and it's actually the value of x, which probability of x smaller than x is greater than or equals to 0.05, and probability of x bigger or equals to x is greater than or equal to 0.05. So over here, median is actually trying to catch up the central places of your probability. So when you're actually having a probability like this, it's trying to cut through at the middle of it. Okay. Mean sometimes will actually get distracted if your if your graph is actually scattered. not to say scatter, it's a skew to the left, sorry, skew to the left or skew to the right. But we'll discuss on this one later in the statistics class, so don't worry too much. But I mean, you should know what's the difference between mean or median, yeah? Then, variability of a discrete random variable. So again, it's the same. You are able to calculate your standard deviation. Okay, you're able to calculate standard deviation using the equation over here, which is based on probability as well. Again, it's actually different from the way that you calculate a probability. But this time I don't derive it, because in the end of the day, when you derive it, it's exactly the same that to the probability that, to the original standard deviation formula that you learned before. It's just that right now, this time they changed to probability format, no longer based on the occurrence that you actually have. Okay, somehow you can understand this way. It's no longer data driven. Okay, because you don't have the data right now anymore, but the behavior of the data is captured using the probability. Okay, so hopefully so far so good. Let me see if there are any questions at the moment. Or maybe yes. One of my friends requests to join the team but can't join the meeting. You can invite a friend to other participants. Oh, okay. Let me see, are there anyone that's joining? Okay. Why they are still joining at this moment? This is weird. I just accepted. Okay. Yep. I just accepted the rest of the join request. So really make sure your peers are around, yeah, because you must try to help each other right now, because even I am not so sure whether the list I have in the Microsoft team is identical to the one that we actually have in the Spectrum or not. I will only get the latest name list today, hopefully, because the end probably is just ended and we have class 9 a.m. So I can't really update or cross-check the list from Microsoft team as well as the list from the Spectrum, or the one that is actually registered based on different groups. So hopefully next week onwards, everything will be settled down and I can trace every single one of you somehow. Then let's continue. So we move on to binomial distributions. So previously, what we actually discussed is in general how a probability distribution should look like. Okay. And right now we are talking about a very specific situation of binomial distributions. How binomial distributions can actually help you in certain kind of scenario, right? So a binomial experiment is one that possesses the following properties. You actually have n repeated trials and actually a fixed number of observations. Okay, and this fixed number is always like from the beginning. For example, you have 15 toss of coins, you have 20 patients, you have 1,000 people surveyed, so you know that there are a set of observations, a set of trials, a set of actions. Sometimes when I'm explaining, I'm using the word action that is actually been executed. Okay. So in that case, each trial results on an outcome that may be classified as a success or a failure. Hence the name binomial. You only have two possible outcomes. Okay, so only two outcomes. So for example, if it's a coin toss, very straightforward. It's either head or tail. Two possible outcomes. That's it. If it's a patient, maybe the things that you want to measure is does he actually having fever or actually no fever? Success or failure? Okay, yes or no answer. And then 1,000 people survey on a specific, or maybe whether in the morning they are taking nasi lemak as a breakfast or not. Okay, or not. So you will notice that the things that you are actually measuring is most of the time yes or no answer. Because only most of the time, yes or no answer can be helping you to get only two outcomes. Of course, if there's a special cases like coins. Coins only have two possible outcomes, then you don't really need to do yes or no. I mean, you didn't need to convert into yes or no. But how about dice roll? Dice roll, there's always like six different outcomes. But can the dice roll be modeled in binomial distributions? There is a possibility when you are actually capturing the probability based on, for example, here, rolling 6 and comparing to not rolling 6. So in that case, your success cases for rolling 6 is actually 1/6. Failure cases for rolling 6, which is 5/6. Okay, so hopefully right now you are very clear on the binomial distribution. Success or failure, only two outcomes over here. So the probability of a success denoted by P over here remain constant from trial to trial. So what is the specific example? What is the specific probability also over here is independent. Every time when you're tossing a coin, it's actually doesn't affect your outcome to the next round, right? Every time you're asking the patient is actually you're actually having fever or not, okay? You don't really affect your next outcome, right? And so on. So probability of success is actually P, probability of failure is actually Q minus 1P. So you have a very clear cut of probability values over here. Your success is P, probability of failure is Q, where your Q can be calculated using 1 minus P. Because why is 1 minus P? Still remember your multiplication rule or your complement rule? Success or failure. These two are exhaustive events. So in that case, it's either success or failure. That's why when you actually know the probability of success, you'll be able to know the probability of failure by doing 1 minus on it. Complement. You still recall. All right? So you flip a coin 2 times and count the number of times the coin land on head. So we try to do some case study over here. We try to justify why is the binomial distribution, because why? The experiment consists of repeated trials, flipping a coin, and you're flipping it 2 times. You can flip 5 times, you can flip 10 times, you can flip 100 times. So this one is repeated trials. Each trial can result in only just 2 possible outcomes, which is 2 possible outcomes over here, head or tails. The probability of success is constant, 0.5 on head, 0.5 on tail. Okay, and every trial is gonna be the same. It's not like, oh, next trial you're using different coin and that coin is biased coin and becomes 0.4 times 0.6. No, binomial distribution have this this strict rule. Every time your probability of success is constant. Okay, and why? How to make it constant is the trials are independent. Getting the hands on one trial does not affect whether we get hands on other trials. All right. So these are the 4 things, but eventually it's only 3. Because over here, these 2 are actually coupled together. Okay, for the probability of success to be constant, the trial needs to be independent. All right. So this one, this slide is basically tells you in a much more formal manner in terms of definition. So suppose there is an n independent experiment. You have n over here and perform, where n is a fixed number, and that each experiment results in a success of probability P and failure with probability 1 minus P or Q, if you still remember, the Q over here, Q. The total number of success, X, okay, is a binomial random variable, parameters N and P, okay? So we are writing over here is X, B, and P, okay? So this one is actually a simplified form in writing it. X is distributed binomially with parameters N and P. Why Q is not inside? Because Q can be calculated using P, so you don't really need another parameter or another variable for it, right? So the probability distribution of random variable is called a binomial distribution. So this is how the binomial distribution is supposed to look like, all right? And there is a formula for you to remember, which is this one. Of course, after all the explanation over here, all this explanation is for you to tell you how actually binomial distribution works. But in the end of the day, binomial probability refers to the probability that a binomial experiment results in X success, and this is measured using these formulas. So the first thing you have, this one is actually combination. Sometimes you might write in this way. It's actually the same, yeah? Just that this time I'm writing this way. So there's n, which is equal to the number of trials. There's x equals to 0, 1, 2, until n, because it depends on how many times you actually want to measure, how many successes you actually want to measure. For example, if it's the number of coins tossed just now, after you flip 10 times, how many times what's the probability I will actually get 3 hits? In that case, your n will become 3. Sorry, your x will actually become 3. Then, the probability of success in a single trial. So this one is already mentioned to you. If it's using a coin example, it's 0.5. The probability of failure in a single trial, again, Q, is measurable by calculating 1 minus P. So this one is actually replaceable. Okay. And if we're using a coin example, it's 0.5 again. Then this one is actually the combination of n items taken R at a time. You have already learned about combination, so you're supposed to know this formula as well. And probability of X gives the probability of success in n binomial trials. Okay. So this set explains how this the binomial equation works. All right. Of course, there is a special case when you actually heard about Bernoulli. Why Bernoulli? Sorry. Bernoulli distributions. If there's only one trial with probability of success P and probability of failure 1 over P, this is actually exactly a binomial distribution, right? But specific cases, you only have one trial. So in that case, this is called a Bernoulli distribution. Special case of the binomial trial with n equals to 1 and probability of success is P, probability of failure is Q. That's why everything when you put in 1, 1, 1, 1, 1, in that case, it will become P somehow. So yeah, success and failure. So what you need to understand over here is Bernoulli trial is a special case for binomial distributions, because these two are almost the same. It's just the difference is binomial distribution trying to measure 2 or more trials. Bernoulli trial measures 1 trial only. Okay, because why? The calculation over here. I already demoed the example over here actually. Okay, we go into the example. Suppose a die is tossed 5 times. So what's the probability of getting exactly 2 falls over here? So from here, you know that a die is actually tossed 5 times. Why a die is the horse? I think it's roll, okay? What's the probability of getting 2 falls? So number of trials over here is 5 times. So you have n over here. What do you want to measure? It's actually 2. So you actually get this value over here. So you know what is your n and what is your x right now. The probability of success of a single trial. Right now you are measuring 4. Okay? Because right now you need to be clear that the probability over here is dependent of the action that you have. If I'm changing the question, what is the probability of getting 2 exactly odd numbers? So the whole probability is actually different, you know. The probability of success in a single trial from 1 over 6 become 1 over 2. Because probably for you to get odd numbers, it's actually 1 over 2. You have 3 chances out of 6, right? So you need to be very careful on what is your things. What is the events that you want to actually measure over here. But again, we go back to this example. For you to get an outcome of 4, your events is your probability is actually 1 over 6. Probability of success on a single trial is 1 over 6. That's why you're getting this one, which is your P. And then for you to measure binomial distributions using X and your parameter is N and P, you can rewrite in this way. But the main thing is actually this one. Okay? Because once you have this equation, what you need to do is you have n, you put it inside. You have x, you put it inside. You have p, you also put it inside. And how do you get your q? 1 minus p. How do you get your x? From here. How do you get n minus x? Again, it's from here to here. So whenever you are able to identify n, x, and p, you'll be able to slot in all the values over here and get the answer directly. So when you go into calculations problem on the binomial probability, the key point over here is for you to identify NP. Then basically you're safe. Of course, sometimes I was saying the NPQ as well because you should, but because you can calculate Q using P, but it's the same thing. Because NPQ, and then you'll be able to get, and also, of course, the X as well, okay? Because the X is actually the things that you want to measure, right? So once you slot in, you get the answer nicely. Another example. So I think this example, I didn't give you the answer, but hopefully you have tried on it. So a coin is thrown 10 times. X is a random variable representing the number of heads obtained. So what's the probability of getting 2 heads and 8 tails? So the probability of throwing a head is 1 over 12, 1 over 2. How am I able to tell this? It's a fair coin, right? Because I don't really tell all these biased coin. So in general, it's going to be a fair coin. And the probability of throwing a tail is actually 1 over 2 as well. So therefore, the probability of throwing 8 tails is actually 1 over 2 to the power of 8. Okay? Hence, the probability of throwing 2 heads and 8 tails is over here. Okay, are you following? Hopefully you are okay. It's almost the same. You just, again, need to identify N, P, and then you get your Q. What's your N? 2. What's your P? Sorry, N is not 2. Sorry. N is 10. P is 1 over 2. Q is 1 over 2. And what do you want to measure? Okay. Again, this one, hopefully you will get the answer in a very, because it's actually quite straightforward. Once you are able to capture this answer, capture the patterns or capture the correct variables in the questions, then binomial distribution is not that difficult to solve. Again, another example, eggs are packed in box of 12. The probability that each egg is broken is 0.35. Oh, okay. So over here is broken or not broken. Remember your exhaustive rule? Yes or no answer. So in that case, find the probability on a random box eggs there are 4 broken eggs. So your N is, before we are looking into this, okay, N and P and Q. 12 is your N. 0.35 is your P. One thing you need to be careful is sometimes the probability that each egg is broken, right? Over here his writing is broken. Maybe the question maybe will give you the probability that each egg is not broken is 0.35. And then it's asking you the probability for a random eggs there are 4 broken eggs. This is the thing that you need to be careful. And think about it, how you actually kind of solve this kind of situation. Of course, the tutorial have these kind of questions. You will try later. We go back to these questions. Again, N is 12, your P is 0.35, your Q is 0.65. All right, and the number you want to measure is 4. So X is actually 4. So pushing into over here, again, using the same formula, you'll be able to get your answer. Okay. So the key point over here is, again, identifying your N, P, Q, and eventually X from the question. Okay, we move on to cumulative binomial distributions. A cumulative binomial probability or distributions, this refers to the probability that a binomial random variable falls within the specified range. Just now, we actually have some example. We are actually using a comparison in terms of X bigger or something, or X smaller than a certain values. In that case, it's actually given a range, okay? And this particular range, you will need to sum up all the probability together that is actually fall into that particular range. For example, you have a 100 coin toss, and then you actually want to calculate X smaller or equals to 45. And then your P is actually 0.5. You still recall the way binomial probably is written. So you need to sum up when x equals to 0, when x equals to 1, plus a lot of times, plus x equals to 44, plus x equals to 45. Because you are measuring smaller and equals to 45. You need to sum up all the possibility over here. So again, simple example. You're given the following. You have number of x equals the number of boys in the family. And then NP, why they are showing you this one first is because this is a random variable, okay, that you want to capture. N equals to 6, P equals to 0.5215, so you know that Q is 1 minus 0.1215. 0.5215 equals to 0.484785. So what proportion of Singapore families with exactly 6 children will have 3 boys? So from here, you have at least 3 boys and not only 3 boys. Before we move on, we already know that NPQ over here. But this time, we are actually calculating this one. So in that case, or this one. So in that case, we need to calculate x equals to 3, x equals to 4, x equals to 5, x equals to 6 individually, and you sum them together using a probability of x bigger or equals to 3, equals to this one. Why you know that you need to stop at 6? Because the maximum number that you have is actually 6. Okay? Or you want to do another way around, which you can use a complement rule, and then you try to change the way that you calculate to become 1 minus x equals to 0 plus x equals to 1 plus x equals to 2. The good thing about here is you calculate one less binomial distributions. This one you need to calculate 4 times. This one you need to calculate 3 times only, right? But both of the answer will be the same, all right? Again, we go back to the 8 example, but this time we are doing a cumulative distribution. So you notice that your n is the same, 12. Your 8 is actually having the probability the same, 0.35. But over here, he's actually asking you to measure there are less than 3 broken eggs. So in that case, you actually measure in this way, probability of x smaller or equals to 3 because it's less than. Right. Sorry. Why? This one is supposed to be probability of x less than 3. Okay. You see, there are typos, so we need to fix it later on. That's also the reason why, because the equal sign is not here, so you don't really include 3. All right. So again, you need to calculate over here. And then when you are expanding it, it depends on you whether you're putting this one or not. And in the other day, you get 0.0151 for your answer. Okay. All right. And means and variance. If you still recall, we are actually talking about means and variance previously on how the shape, it will actually affect the shape on your probability distributions. So in that case, in a binomial distribution, you actually have a easier way for you to calculate your expected value, which is your mean, by getting n times p. It will become your mean. And also variance, you times n, you actually calculate n times p times q, or n times p times 1 minus p. Okay, it's the same. Standard deviation, of course, is you're just doing a square root on it, or a square root of NPQ. Okay, or a square root of NPQ. It's the same. Okay, then we move on to Poisson distributions. Let's see. So far, so good. That's a question. Okay. Okay, let me see. Nothing. Just need to accept some. All right. So we move on to we move on to the Poisson distribution since there is no question at the moment. I'm actually expecting you. If you have any questions during the lecture, you can just type it in the message. Then I can actually answer on the spot during every single stop they'll actually put in. So right now we go to the last session. I do it a little bit fast today because I will need to end the lecture a bit early. I have something else to attend later on. But I actually ask you to do something for the next 1 hour, so don't worry too much. Because there are things that you're supposed to do. Again, we move on to the Poisson distributions. I just want to finish the class first. All right, right now. I know that I'm moving a bit fast. So next week, I will actually do another 1 week of 1 hour of live lecture. I just want to wrap up all the things from the first 4 weeks, because first 4 weeks is more on calculations on the probability concepts. Okay, we move on to Poisson distributions, like the binomial distributions. So these are these numbers are whole numbers. So and such a random variable is a discrete random variable. So in Poisson, almost the same with binomial. You are actually still getting integer or integer-like values outcome as your discrete random variable. Okay, you have a fixed outcome, fixed number of outcomes. Unlike the binomial distributions. So what's the difference over here? It's an infinite random variable where there's no upper limit. Previously, when you are actually calculating in terms of the binomial distributions, for example, dice roll, you will always have something called range, like dice roll 1, 2, 3, 4, 5, 6, bounded outcome. Number of fours that you can get after 10 rows. Okay, 1, 2, 3, 4, 5, 7, 8, 9, 10. You know that the range is actually having an upper limit. But in Poisson distribution, the way that we actually design the Poisson distribution is to cater special events. Special events as in some rare events that is actually rare, very, very rare to happen, but it can happen. Okay, for example, over here, there's no upper limit for the number of cars passed under the bridge. In general, okay, given the time period, maybe 1 hour, the number of cars that pass through the bridge is usually fixed, as in maybe 100 cars or 1,000 cars. But there is a probability that if one day there's a traffic jam or there's a car accident just right in front of the bridge, okay, so in that case, you actually have that particular timing having a lot of cars, okay, passing. The example is actually passing under the bridge, right? You have a very rare situation where the time for you to take to pass through the bridge is actually much longer than usual because of traffic jam, right? So in that case, when you're measuring the time for you to pass through, there is actually no upper limit. Okay, and this no upper limit, right? This so-called no upper limit over here is to cater special cases that is actually happen rarely. It's not gonna happen all the time. That's the reason why when you are looking at the Poisson distribution, kind of the shape of it, when your values, okay, when the values of the potential outcome is going higher and higher and higher, the probability gets lower and lower and lower, but it will never reach zero because it's trying to capture rare events. Although the rare events is actually very hard or no, will not almost not ever happen. But again, because it's a rare case scenario, it's capturable by the Poisson distributions in terms of this probability. So in the binomial distributions, we have NP, but in Poisson we only have one, which is lambda. The lambda also tells you average, mean, expected value. It's the same. All right. So how many events we should expect in that particular time range? Yeah. So in the binomial distribution, each flip is independent. And in the Poisson distribution, an occurrence happening at one time interval is independent of another occurrence happening in a different time interval. So you need to consider in the way that time interval based. In the Poisson distribution, you always you try to measure in terms of a time period, maybe every 5 seconds, or 5 minutes, or 5 hours, or 5 days, and then you compare it another 5 days, or 1 day, and so on. Okay, so within a particular time period, if your events are actually happening within the particular period is actually dependent. But when you are comparing from one time period A with another time period B, okay, for example, if I try to draw, you have a time period A with another time period B. Okay, so in that case, these two are actually independent. So some of the probabilities of a Poisson experiment can be hard to identify. Generally, what you need to consider is the experiment is concerned counting number of rare events. Again, we are looking at the shape is almost like this. Of course, it's this one is actually a Poisson distribution, so it's supposed to look like this. Okay, and then it will actually keep dotting until infinity. Okay, but if you try to try to just illustrate that, I'm not telling that it's a continuous distribution. It's supposed to look like this, almost roughly, yeah. Okay, it will go down. It will always not touch the line. Okay, whenever your x-axis is going larger and larger, this part of the probability will still exist, but it's going to be very, very small. And this is the part that we are talking about capturing rare events, because most of the time the events is going to be under this range, maybe where this range is almost similar to a normal distribution, but they are this range over here that is actually trying to capture rare events. Okay, and this rare events still occur randomly. All right, and intervals between rare event are independent and do not overlap. Yeah, so this one is actually explained over here. Then we continue on. Explanation. Suppose you have, this one is a definition, yeah. Suppose you have a stochastic system. Okay, stochastic is probabilistic, it's the same meaning. Just sometimes they have a fancy words. In which events of interest occur independently with small and constant probability Q is called a Poisson process, right? And then a Poisson process is a stochastic process which events occurs continuously independently. It's actually the same thing. And the name comes from the Poisson, French mathematician, Simon Denis Poisson. Okay. So over here, rows of the Poisson distributions. Examples given here is actually quite general, actually. It's used in quality control settings to count the number of defects of any item. We are actually expecting defects in a conveyor belt line in the factory, but we also consider this one as a rare events because why? Because why? We are not expecting the defects to be happening all the time, right? So in that case, Poisson distribution is actually a well-designed function for it to capture so-called rare defects. Then in biology, to count the number of bacteria, okay? Because again, there's a rare cases that maybe is actually corrupted, and then you have now a big number of bacteria. In physics, to count the number of particles emitted from radioactive substances. So it's actually applicable to many places. Let's see what is the Poisson process and the Poisson distribution over here. This one is again terminology. The number of airline crash next year. The number of people arriving at drive-through window in the next hour. The arrival of an email of your inbox. When is the next arrival, for example. The number of light bulbs removed from our inventory today. You will notice that all this, right, is actually having a time for you to capture. Okay? They are all in terms of number on a certain occurrence and a certain interval of time. Okay? And it's all described by a random variable. All right? So we consider this one as a Poisson process. Okay, and that's why the things that we are actually discussing just now is a Poisson distributions, right? But when we are talking about the collections of data on the random variables where the x is the number of events that have occurred up to time t, this thing is considered Poisson process. This is Poisson process, this is Poisson distribution. These two things, because sometimes I see there are students confused. If you're still confused, there are some notes over here. You try to capture the meaning of it. Poisson process is the model. Poisson distribution is actually the probability distributions to tell to tell the behavior of the data looks like. Okay. Oh, come on. Okay. Okay, now, after the theory, we move on to the calculations. The Poisson distribution is a discrete probability distribution for the counts of events that occurs randomly in a given interval of time or space. All right, so this one basically, after you have gone through a few slides, you can roughly capture. We already mentioned why is it discrete, why is it occurs randomly, again, random variable, and it's a given interval of time. This one is a key, very, very key difference compared to what we have in a binomial distribution. If you still recall, binomial distribution, NPQ, right? But this one only having one lambda. And if we let x, number of events in a given interval, equals to number of events, and then if the mean number is actually given lambda, and the probability of observing the x events will become like this. And why we actually can have this kind of curve, okay? It's because there's an exponential constant over here. Of course, if you study about maths, then you know the exponential constant is actually the shape of it, all right? Then, exponential is a mathematical constant, approximately 2.71828 and so on. And the probability should write in this way, similar to the bin over there. This one is actually a Poisson, writing as PO, okay, or 0. Previously is BIN, right? And then lambda is a parameter of the distribution. So again, we try to compare just now, as I mentioned. NP is the one that is a parameter for binomial. Lambda is a parameter for Poisson. And then we say x follows the Poisson distribution in the parameter lambda. And the Poisson random variable can take any positive integer value. So, example 1. The birth in the hospital occurs randomly at an average rate of 1.8 births per hour. So what is the probability of observing 4 births a given hour at the hospital? So you notice that this timer is actually giving you certain kind of decimal points. But it's possible because why? After you are actually having an average in terms of hours, it's possible that the average value of it is actually having decimal values rather than it's always integer. Okay. Even though in general you can't have 1.8 birth, you can have 1 birth, 2 birth, 3 birth, and so on. Because basically this one is your outcome as a random variables. But in average, okay, you are actually able to calculate in decimal points. So x equals the number of births in the given hour. Event occurs randomly. Mean rate equals to 1.8. So probability of x equals to 4. Okay, equals to exponential negative to the power of negative 1.8. Just following the formula that you actually have over here. Plug in 1.8 inside. Plug in 4. 1.8 is also here. Plug in 4. So you get 0.073. Okay. So given the mean that you actually have, you are able to estimate the 4 births in a given hour. You notice that this hour and this hour is actually the same. The time difference is actually the same. Okay. How about example 2? What about the probability of observing more than or equals to 2 births in a given hour at the hospital? Oh, this is a problem for Poisson distribution. You will not be able to measure infinite numbers of it, but you are still being asked these kind of questions. I mean, what's the probability for you to observing more than 2 or equal to 2 births in a given hour? So in that case, how are you able to do it? You are using a complement rule over here. Whenever you are calculating a Poisson distribution problem, and you need to calculate a probability bigger than a certain range, okay? So in that case, you need to use a complement rule. to calculate another way around. Okay, like the example that I draw just now, right? You are actually asked to calculate this one, but for you to calculate this probability distribution, you need to keep calculate, and the limitation of the Poisson is you wouldn't have n, you wouldn't have n point. But the good thing about Poisson is actually you can actually calculate this part of it, right? So in that case, you just do 1 minus of this part, right? Then you are able to calculate the probability of 1 minus of this part. Then this one is equals to, yes, remember your complement rule. So that's the reason why you are able to solve this problem by changing using the complement rule, and you will be able to calculate this. Okay. And when you are changing the direction, you need to be careful. When this one is actually more than or equal to 2 above, you have an equal sign. When you're changing your direction, then your equal sign is gone. Okay, sorry. And then for it, and then you basically can just solve it directly, and you get the answer. And the last, second last, I think. Oh, a few slides more. So a car enters a bus circle having an error ratio of 20 per minute. And what's the probability that in the next minute we'll have actually 10 cars? Again, you just log in. Almost the same. So this one is actually not that difficult because it's again per minute and per minute. So this one is even harder. This one is even simpler. So actually these 3 examples have already give you some basic idea on the Poisson distribution. Then you have Poisson mean and variance. Again, mean equals to lambda, variance also equals to lambda. Standard deviation equals to square root of lambda. So Poisson distribution, that's the reason why Poisson distribution can be represented by the lambda itself only. And even when you're measuring the mean and variance is also controlled by the lambda. Okay, the key challenge on on the problems on Poisson distribution is changing time intervals. If you notice that just now we are actually discussing on example 1, per hour, given hour, same time interval. This one is almost the same. And then this one, per minute, next minute. You notice that the unit is the same. But when you are actually changing the time intervals, on average, a certain store have a 0.2 shoplifting incidents per day. What is the probability that there are 2 shoplifting accidents in the 4-day period? From per day, change to 4 days. What do you think it will change in terms of your lambda value? In 4 days, your lambda basically happens 4 times, right? So in logical speaking, you know that, you need to do a times 4, which is correct. Okay, so for you to have 0.2 incident in 1 day, then there are 0.2 times 4 incident in 4 days on average. So that's why you get 0.8 over here. You are changing your lambda value based on the period that you actually have over here. So if the x is the number of shoplifting accidents in the 4-day interval, then probability for you to have 2 shoplifting incident is actually exponential of to the power of -8 times 0.8 to the power of 2 divided by 2 factorial, and then you get 0.144. Okay, so this is how you actually change your lambda values based on the time interval, right? Then, if new cases of West Nile in New England are occurring at a rate of about 2 per month, and what's the probability for that exactly 4 cases will occur in the next 3 months? Again, 2 per month, next 3 months, you add another 3 months, right? So in that case, your lambda is actually over here is 2 per month. But you are changing to 4 in 3 months. So in that case, your lambda value is everything times 3, right? 2 times 3 over here, 2 times 3 is over here, or you want to put directly over here 6. By telling that 6 per 3 months directly. It's also fine. Okay, but in the other day you get the same answer. If it's actually 6 cases, you are just changing the x value, right? So nothing to do with your lambda value, but you change your x value and then you basically increase your probability. Okay. That's all for the class. Okay, I actually go through very fast. Okay, so in that case, if you have something that's not understand, please ask. Okay. Okay, still no question from the floor, so it looks fine for me. Although, if you are just focusing on the equation over here and also the special cases that you need to cater about, still quite manageable. Okay, but I would strongly suggest you to go into the tutorial that will be released on Wednesday. Try yourself, and also see whether you can solve it by yourself. Really, all right. And then one more thing is I want you to do during the next 1 hour is in your spectrum. There's actually tutorial 2 is still here. Group project. Spend the next 1 hour to study about the group project. Okay? See? Something wrong. Wait. This one is your group project, right? Spend the next 1 hour to study about the group project. And then why it didn't open in a new tab? Okay, never mind. Study about the group project. Be very careful on the content inside. Study about the rubrics, and also study about the questionnaires guide. I will talk about this one more in the tutorial class, and also next week I will emphasize more, because in the next 1 hour, after you have done all your readings over here, I will need you to find 5 to 6 in a group. Okay, in the next 1 hour, we have plenty of time to do this. Okay, I'll click this one again one more time. And remember, take your attendance, yeah? And okay. Because it's 20 marks. And then you have reports and you have presentation as well. And make sure that your group members is from the same tutorial group. 5 to 6 members only. 5 to 6 members. There's no 4 members. Okay? 5 to 6 members. So please try to make sure that your group members are fall between this one cases. And the first part is actually talking about questionnaire, which you're supposed to be able to complete the questionnaire as soon as possible and try to do it before you actually start the SPSS. Okay? Again, I haven't really told you how to do it, of course, but have some idea on the questionnaire and also the topic of interest first. What are the things that you want to investigate within university or within Faculty of Computer Science? The examples are already given to you. So the first thing that I need you to do for this week is 2 things. One is topic of interest. Another one is find 5 to 6 of group members. These 2 must be done within this week. All right? And then, if you have extra time, try to come out some sample questionnaire, which is, I showed you an example in here. Topic, addition of social networking science, and then you actually have this kind of, all these kind of things over here. Okay? All right, please take a look. And that's all for today. If you have any questions within this 1 hour, please also, you text me directly. Of course, I'm going for a meeting right now, but I'll reply your questions very soon. Okay, so again, that's all for today. Thank you. Let me come back over here and see if there's any message or not. Yeah, no message. It's the same thing. So that's all for today. So make sure you are doing the task. I mean, I end the lecture earlier doesn't mean that you don't really need to do the group project and so on. Please don't come back and tell me, oh, you don't have time to find group members and so on. You have 1 hour right now. Please go and find your group members. Okay, so that's all. Thank you very much.
Okay, thank you, Doctor.
Thank you.